All right, so now we're working on hyperbolas. You can read the definition there, and the picture that's there should be helpful in understanding that. This time the two fixed points called foci will be measuring the distance from the focus to a point on the curve, and then from that point on the curve to the other focus. And the difference between those two distances that we measure will always be the same for any point on the hyperbola. I wouldn't get too wrapped up in the vocabulary of, it's called the transverse axis, that contains the 5 major points, the 2 vertices, the 2 foci, and the center. Kind of nice to know that if you are ever in a trivia game, but otherwise it's probably not as important as you might think. And again, what I'm going to do is I'm going to skip a whole lot of the discussion on how this is done, from the center being first is always at 0, 0, and then moving to other places. Like I did with the ellipses, I'm going to skip to the good stuff. So let's go with that. So you can have a hyperbola that points left and right like this, or it can open up and down. Those are the hyperbolas that we're going to be dealing with. And so the vertex is for each of those branches. The furthest most point kind of reminds me of a parabola, but I will tell you the curvature on the hyperbola is very different from the curvature of a parabola. You can never get one to overlay the other perfectly. But those are the vertices, and I'll mark the vertices on the other one as well. And then the center is exactly halfway between the vertices. And then there are foci, like the parabola, points that are kind of inside of the cupping, if you will, of each branch of the hyperbola. And all 5 of those points are collinear. The distance from the center to a focus is still going to be called C. So the center to focus distance is C. The distance from the center to a vertex is always A. Let's see where I can draw that so it makes sense. Do it up here, I suppose. That's A. And this distance from the vertex to the center is A. Now, there's a perpendicular distance that's probably not obvious to you, because at this point you don't know why in the world you would need another point. But there are a couple of points that we could draw in. They should be equally spaced. Sorry, these are symmetric figures, so I'm trying to make them look that way, but sometimes imperfect. And the distance from the center to those points is B. So right now you don't really know what B is, how do you get it, how do you measure it, and that's fine. We'll get there eventually. But there is a thing there that you would not know anything about, and we will cover that. Now, of those 3 lengths, you should see that C is the longest. And so if I were to pull on either case the B value, and right now I'm kind of looking at the right-hand one, so it's a horizontal thing. It could have been vertical instead if I were using the first of the 2 hyperbolas that I drew. So with that given, A is going to have to be perpendicular to it. And as it so happens, kind of like what we saw with the ellipse, the length of C is always exactly long enough to form a right triangle. And because of that, the focal length C, the hypotenuse squared, will always be leg squared plus leg squared. And so this will be what allows us to solve for C, the focal length, when that's part of the problem. Notice that this is the sum of the two distances squared, whereas for the ellipse this was C squared equals A squared minus B squared. Now, unlike the ellipse, A and B have no specified relationship. A could be longer than B, A could be shorter than B, A could be the same as B. The only thing I know for sure is because it's a right triangle, C is definitely longer, and it's the hypotenuse of a triangle using that A and B for a given problem. So, now when we're talking about these, let's look at the first one. I am again going to use the X radius and Y radius. And so in this particular case, the radius for X is the same thing as A, because it's the way we're moving horizontally from the center to the vertex. And here R sub Y is B. That's how far we're moving in the Y direction. In the other situation, R sub X is B and R sub Y is A. And again, we've got a little bit of confusion about, YA, YB. They're going to switch roles, and I think you'll find if you use the X radius and Y radius for graphing purposes, that's what you need to know. It's what you need to have correct, and it won't matter if you know that that's supposed to be A or supposed to be B in this problem. And if you're solving for C, look at that equation. A squared plus B squared is going to be equal to the square of C. If you added A squared plus B squared or accidentally added B squared plus A squared instead, would it make a difference? No. Those two sums would be the same. So the order in which you write those, because you're adding, it doesn't matter. So you'll just add the squares of those two radii. One of them's technically A and one of them's technically B, but I don't think it's going to really matter that much. And you'll see why later that this is a real benefit to us to be able to do this. So again, we could come up with a distance formula derivation of the basic equation of the hyperbola, and we could go through all that. I don't think it's worth our time, so I'm just going to cut to the chase and say here they are. They're actually two. This is going to look familiar. We're going to have x minus h squared divided by r sub x squared, and we're going to have a fraction y minus k squared over r sub y squared, and those two fractions are going to be in an equation where somehow that's equal to 1. So all of that looks just like an ellipse, and you're thinking, well, what's the difference? Well, the difference, my friend, is this. Instead of an addition between the two fractions, it's a subtraction. I know, very bad pun. The difference is, yeah, you get it. So the thing about subtraction in this equation is that the order in which you subtract does matter. If you do 10 minus 4 or 4 minus 10, the order in which you write those is very important to get the answer you're looking for. So the key here is, and I'm going to write the other equation, the key here is which variable is in the place where it has an understood positive coefficient. I'm going to refer to the first fraction in front of the subtraction as the positive fraction, and the one behind the subtraction, I'm going to refer to it as the negative fraction. And the variable that's in the positive fraction determines everything on the hyperbola. So we've got to have two different versions of this. Like I said earlier, 10 minus 4 or 4 minus 10, those are two different things. So what difference does that make? Besides the obvious bad pun that I made earlier, the difference is that the positive fraction tells you which way to go for the major things. If x is in the positive fraction, that means that you're going to go in the x direction to get to the vertices, to get to the foci, and your hyperbola will open to the left and and to the right, because all of the major things are happening in the x direction, and I can tell again that that's what it is because x is in the positive fraction. Okay, so you might have kind of gleaned that what's going to happen with the other case is if y is in the positive fraction, we're going to move from the center in the y direction for all of the major things to happen. So we'll go up and down for the vertices and the foci, which will make our branches open up and down. All right, and so we would use the equation c squared equals a squared plus b squared to find the length of c and locate the foci as needed. Just remember, let me draw those in, that the foci and the vertices are all collinear, and because of symmetry they are a standard distance from the center either way, and all 5 of these major points are collinear. Now, there's one feature of the hyperbola that I have not yet mentioned, which now's a good time to do that. The drawings that I've been doing aren't good, and you'll see why in a second. It's kind of a good indication of what's supposed to be going on, but the drawings I have don't do what I want you to see. So, at any rate, remember these come from cones, double napped cone, that are involved in the construction of these when you intersect the planes with the cones. So what happens is the edges of the cone are actually going to serve as asymptotes for the curve. And so there are asymptotes involved in this problem. And like I said, my picture is not very good. But if you'll notice that as I'm trying to draw these in, it's supposed to be a line. Not sure that's actually straight, but use your imagination. There are 2 lines that are going to be asymptotes for the 2 branches of our hyperbola. And the thing that we need to realize about them is that, first of all, they intersect each other at the center. And so if we wanted to find the equation of those asymptotes, we're going to use the point slope form. And the point that we're going to use is the center. So the point in the point slope form will always be the center, HK. Now, if you recall, let me first talk about the point slope form. It's a really good form for you to know to find the equation of a line. It will always be y minus the y coordinate of the point you know is on the line equals m times x minus the x coordinate of the point you know. And there is the point slope formula for the equation of a line. Keep in mind our point is going to be hk, so I'm going to take out x sub 1 and y sub 1 in a moment, put h and k in their place. And then let's talk about the slope. If you recall, just a few moments ago we were talking about this distance that you're going the other direction, the perpendicular direction to the transverse axis. So the foci, vertices, and center are all collinear. If I were to go off in the perpendicular direction a distance of b, then it turns out, I didn't draw that quite right. Oh well, we'll use the top one anyway. As it turns out, to go from the center to another point on the asymptote, if you go a rise of r sub y and a run of r sub x, see if I can draw that in so you can see it. We're going to rise r sub y and run r sub x, and that will always give you another point on the asymptote. And so the slope of the asymptote that goes upward is always rise r sub y over run r sub x. Notice I'm not saying a and b, because sometimes the slope would be a over b, and sometimes it would be b over a. And so then you'd have to kind of know formulaically, well, which one is it this time? Is it a over b, or is it b over a? Instead of having to make that decision, it's easier if you've already called it r sub y and r sub x, that slope will be r sub y over r sub x, no doubt about it. Now for the other one, we're going to go the same distance, but this time we'll move r sub x to the left. So what that's going to do to us is give us a negative slope. Same value, same rise, same run, but just the opposite direction. So the slopes of the two asymptotes are plus or minus r sub y over r sub x. So the asymptotes will have an equation always. This is an always thing, and you should probably commit this to memory. The asymptotes for a hyperbola will always have the equation y minus k, the y-coordinate of the center, which is a point on both lines that are the asymptotes, equals plus or minus the slope r sub y over r sub x. So of course we're getting two lines here with the plus or minus. We're getting 2 for the price of 1, times the quantity x minus h, which is the x-coordinate of our point, the center. All right, so that's something you need to memorize right there. So I should probably draw boxes around the things you're supposed to make sure you know and commit to memory, because these are invaluable for solving the problems and being able to solve them readily and easily. Do keep in mind that there are two different equations for the hyperbolas, and the difference is which way they open, which again is governed by which variable is in the positive fraction. If x is in the positive fraction, it will open left and right. If y is in the positive fraction, then it will open up and down. All right. And then the other equation, I think I already boxed it. Let me just double check that. The equation for C, yep, I did. I boxed it. Now, one thing I want to say before I get away from this, an interesting way to memorize these, because the ellipse and the hyperbolas look a lot like each other. The equation for an ellipse is fraction plus fraction equals 1. For the hyperbola, it's fraction minus fraction equals 1. So when the equation for the hyperbola has a subtraction in it, I want you to look at the equation for C. The equation for C squared has addition. If you think about the ellipse was fraction plus fraction equals 1. The equation for C squared was A squared minus B squared. So the C squared equation has a different sign from what the equation of the figure has. So that should help you, at least I hope it helps you, attach those correctly to the right formula for C, because that's definitely very, very, very important. Okay, so let's see what kind of examples we encounter. Let's see, let me change the color back to what I want it to be. There we go. So our first example is x squared divided by 25 minus y squared divided by 49 equals 1. Since this is in standard form for a hyperbola, fraction minus fraction equals 1, that's how we'll know that this is a hyperbola, even if nobody told you it were. So I would start with, well, what's the center? This is going to sound very familiar, by the way, to what we did with the ellipse. The center is 0, 0, because it's x minus 0 that's squared over there. And y squared is y minus 0 squared, so the center is at 0, 0. R sub x is the square root of 25, and r sub y is the square root of 49. And then c squared is equal to a squared plus b squared. And I actually did pick the right one. Just so you know, the equations always have a in the positive fraction, b in the negative fraction if it matters to you which one is which. So I actually did do that correctly. So nevertheless, if I'd added 49 plus 25, either way I would still get 74. And so c is equal to the square root of 74. All right. It didn't ask me to do all of this, but I'm going to go ahead and give kind of a complete explanation and tell you everything that we might eventually do. This problem just asks us to sketch the asymptotes and graph the hyperbola. So anyway, the asymptotes. The equation for the asymptotes will be y minus the y-coordinate of the center, so y minus 0, equals plus or minus r sub y, which is 7, over r sub x, which is 5, 7/5, does not reduce. I would want you to reduce it if it could be reduced, times the quantity x minus h. X minus 0 is just x. So those are the equations of the asymptotes. And notice I could do that even without graphing, because I've memorized that formula that I have in the box above that you can just barely still make out. Alrighty. So here's how I would go about graphing. Let's set up our field, our x and y plane here. Since we're centered at 0, 0, and my x-axis, our x radius is 5, I'm going to make sure I go at least 5 marks left and right of our center. And r sub y is 7, so I'm going to make sure I go at least 7 marks in the y direction, up and down from the center, which of course is at the origin. Okay, so I'm going to plot the center at 0, 0. Then I'm going to plot the points that are x radius away from the center. So center at 0, 0, the x radius is 5. So I'm going to plot a point 5 to the right of the center and 5 to the left of the center. And I'm going to plot 7 away, 7 up and down from the center, because r sub y is 7. And at this point, you may be thinking, oh my gosh, that looks like exactly what we did for the ellipse. And the next step was to just draw the ellipse through those 4 points. Absolutely right. That much of it is the same. This is where it goes off the rails a little bit. That makes it sound bad, sorry. This is where we differ. If you will draw verticals up and down from the points you got from your x radius. These aren't lines, these are going to be segments. Dotted things aren't going to go on forever. And then from the r sub y points that you got, if you'll draw horizontals from it, you may notice that what I'm doing here is I'm creating a rectangle. So instead of drawing a curve through those 4 points like an ellipse, we draw a box around this. And then, this is actually kind of cool, I think. Then, if you'll draw the diagonals of that box in, notice that the diagonals will go through the center of the rectangle. The diagonal is the asymptote. And of course, there are 2 diagonals for this rectangle, so we'll get our 2 asymptotes by drawing those diagonals in. I will tell you, it is way, way, way better if you do this with a straight edge. Freehand, you can see how bad mine looks, although I'm trying to be extremely careful. That's not going to be perfect if you do it freehand. So get a straight edge when you're doing this for yourself. Okay, now you have to draw the hyperbola branches. The only question is, well, do they open up and down or do they open left and right? If you look at the original equation, it's x squared that's in the positive fraction. So we're going to move in the x direction to get our drawing done. So we're going to open left and right. So what I want you to do here to make it look good is starting at the point, one of the 4 points, the correct one of them. Oh, let me try that again. Can't talk and draw at the same time. What I want you to do there is to draw a curve from there, kind of like a parabola shape, kind of think of that in your head, and just have that go closer and closer and closer to that asymptote. So just do your best. There are ways to make this look better. To get another good couple of points is a good idea. But really, for me, this is good enough. So do your best to just start at that point on one edge of the box or the other. So we're doing the left and right edges because x is in the positive fraction, and drawing our curves that approach those asymptotes. All right, so that's how you do that. Now, if you were asked, you could find, for example, the coordinates of the vertices. Having just drawn them, those are those closest to the center points that were our basic points on the box that we drew. All you have to do is just read those off. Look at the coordinates of those points, and it should not be that big of a challenge. So one of them is 5, 0. The other one is negative 5, 0. So I'm suggesting that you look at your graph to answer questions like, where are the vertices? And things like that, because a lot of times you don't have to memorize a formula to do that, as they will suggest in the book. I would just look at the graph and answer that kind of question. All right. So, very, very good. All right, so I'm ready to go on to another example. As that moves up, the next example doesn't give us the equation already in standard form. So just like what we did with the ellipse, we're going to have to do some algebraic manipulation to get it in that form of fraction minus fraction equals 1. So that's kind of a touchstone for what you want to make sure that you get. So we have 25y squared minus 4x squared equals 9. Before I go on with this one, we've talked a little bit about how do you recognize when you see an equation like this? Is it a circle, an ellipse, a parabola, a hyperbola? I tried to give you indicators of those. A circle, if x squared and y squared have the same exact coefficient, it's a circle. If x squared and y squared have the same sign of a constant in front of them but different numbers, it's an ellipse. If there's only x squared and no y squared, or there's only a y squared and no x squared, then it's a parabola. And here, the coefficients of x squared and y squared have different signs. One's positive, one's negative. So since the coefficient of y squared is positive 25 and the coefficient of x squared is negative 4, that tells me automatically, hey, this is a hyperbola. So I want this to be equal to 1. So I'm going to divide both sides by 9 to make that happen. Oh my goodness, this is that example, a problem I was warning you might happen. Here it is. 9 doesn't go into 25 evenly. And so this is good. This is where we're going to have to say, well, I need to divide the numerator by 25 so that it becomes 1y squared. That means I have to divide the denominator by 25 as well. So that denominator becomes 9/25. And doing the same thing for the x fraction, dividing by 4 in both numerator and denominator gives me x squared over 9/4 equals 1. Okay. So the center is at 0, 0. On this particular one, I am not going to find everything. We did that with the last example and did a pretty thorough job. So I'm really going to follow the directions this time on the problem. Kind of wimping out because of the fractions that are involved. It's hard enough as it is. Okay, r sub y is the square root of the number underneath y squared. That's 3/5. R sub x is the square root of the number underneath x squared. Square root of 9/4 is 3/2. All right. So, to sketch the graph, oh, sorry, that wasn't vertical, but hopefully you'll just forgive me and we can go on. Y squared up here. Or y, I'm sorry, not y squared. All right, so since our radii are really pretty small, I'm going to make my mark of 1 on the x-axis pretty big so that I can see what I'm doing when I'm guessing where 3/5 is and where 3/2 is. 3/2 is not as much of a guess, but nevertheless. So the center is at 0, 0. We're going to go in the y direction, 3/5. So about right there-ish. So up that far and down that far. Then we're going to go in the x direction, 3/2. So about there and about there from the center, both left and right, 3/2. Then I'm going to build a box that uses those 4 points as guiding points for my box. When the box is done, you'll notice that those 4 points are the midpoints of the 4 sides of the rectangle, if you've done it correctly. Okay, so anyway, now try to maybe take a straight edge and draw in the asymptotes, which are the diagonals of your box. And let's get this one over here. Wish I had a straight edge. And I wish the pen always were consistent in how much it leaves in its wake. Ah, well, I can dream. And then remembering that y is the variable in the positive fraction, we're going to use our r sub y points, the red ones in this picture, and draw a curve for each one of those to the right as it approaches the asymptote. So it's a curve that gets closer and closer to that asymptote. Sorry, that kind of looked like a line. This side over here looks a whole lot better. So I might ignore that. And then down below, same thing. Do your best to make it look like it's a curve and is approaching the asymptote. One thing I see a lot, and I know it's something that you're trying not to do, but you're thinking hard about it, and maybe you're thinking about something else. So I'm just going to say that I see a lot of times when people are drawing these, a curve that approaches the asymptote, and then for some inexplicable reason, they then curve away from the asymptote again. Don't do that. It should only get closer and closer to the asymptote, not curl back away. So this is definitely not what you are supposed to do. Okay, don't do that. All right, very good. Oh, to finish the answer, I have to make sure I read the directions every time. It did tell us to find the domain and range, so let's do that now. The domain, if you look at that branch, it will go all the way from negative infinity to positive infinity. So we're going to use every single real number for x. The range, however, doesn't do that. If you think about how far down it goes from negative infinity until you get to the vertex. And the vertex is 3/5 below 0, 0. So The value there is -3/5. So the bottom branch goes from negative infinity until you get to -3/5, and then it stops. And includes that point, so that's a square bracket. Then you don't have any answers whatsoever. Again, as you move up, nothing at -1/5, nothing at 0, nothing at 2/5, until you get to 3/5. This is where the upper branch starts out, and it goes from 3/5 all the way up to infinity. So that's the domain and range. All right, let's talk about the next problem. This, again, is going to be a description of a hyperbola, or some of the parts of a hyperbola, and we're going to have to come up with excuse me. I'm sorry, I got ahead of myself. Excuse me. That example's done. So the next page in the notes gives you the standard forms like I gave you. They're using A's and B's. I use R sub X and R sub Y. At the bottom of that slide, you can see where I say these can be rewritten in terms of the X radius and Y radius, which is what I did up above. So we kind of skipped a bunch of the development of that, and I gave you all of that earlier. All right, so this example. This one is given already in standard form for a hyperbola. It's got the y fraction minus the x fraction equal to 1. All right, so we're supposed to graph it and identify the center and give the domain and range. Alrighty. Well, the first thing I would notice, since it's already in standard form, we can identify the center quite easily. Do you think I was going to say -2, -3? Shame on you. It's -3, -2. Oh my gosh, how did I know? Well, be careful with the hyperbola, because the order of the fractions can be y fraction first, x fraction second. The x coordinate is the number with x. The opposite of what I see there is -3. The y coordinate of the center is with y. And the opposite of what I see with y is -2. Be very, very careful here. It's very easy to accidentally go left, right, instead of x thing, y thing. So be very, very careful here. The y radius is 3. The x radius is 2. And that's actually enough to do the graph. We could have found the asymptote equations. We could have found the foci. All kinds of things we could have done. But we're going to just follow the directions unless they ask us to do more. I think that's probably in our best interest at this stage, time-wise. All right, so our center is at -3, -2. My y radius is 3, so I need to be able to go from there up 1, 2, 3, and down 1, 2, 3. My x radius is 2, so I need to go from there right 2, which I've already got, that's fine, and left 2. I always like to have at least one mark on each part of each of the two axes, so I went ahead and put a +1 mark for x. All right, so in the y direction, I'm going to go 3, so up 1, 2, 3, and down 1, 2, 3. Then I'm going to go in the x direction from the center, right 2 and left 2. Then I'm going to draw my box through those points. So verticals up from the left and right hand points, horizontals from the up and down points. So let me draw that box. Then take a straight edge and draw the diagonals. Which are the asymptotes. And then to draw the branches correctly, look at which variable's in the positive fraction. It's y this time. So I'm going to use the points that I got from using the y radius, r sub y, and draw a curve that approaches each of the two asymptotes above. So this one will open upward, and the other half will open downward. Okay. Hopefully that's clear what's going on there. Okay, reading the directions, I found out that I have yet to do the domain and range. So let's do that here. The domain, we're using all real numbers. And the range, we're going from negative infinity until we get up to 1, 2, 3, 4, negative 5, and we're stopping. Union, and then we're picking up again at y equals 1 and going up to infinity. All right. By the way, if I asked you for the vertices, you could just read them right off of here, right? One's at negative 3, 1. The other one's at negative 3, negative 5. So that's supposed to be something that once you have the graph done, I could find that. And if you needed to find the foci, you'd find the value of c, and from the center go up and down, because we went in the up and down direction to graph our branches, and we would get the foci. I think we're going to have an example where we actually do that here in a few minutes. All right, the next one. This is where I was getting ahead of myself. This time we're given information about a hyperbola and we're asked to find its equation. So anytime I'm given graphical information, for me, I've got to draw a picture. This is just a sketch to get my mind going. It's not going to be something I'm grading, but it's going to be something that helps me get my mind wrapped around what's going on. So the center is at 1, 2. I have a focus at 6, 2, 3, 4, 5, 6. Let's see, pick a color for the focus. Let's make the focus that color. 6, 2. And the information I can get before I go any further is the distance from the center to the focus is always called C. So if you have graphed it, you can just count. It's over 1, 2, 3, 4, 5. So C is 5. Otherwise, you could probably memorize some kind of formula that would give you the answer of 5. But I think just having graphed it and count over is probably the smartest thing to do. The other piece of information we're given is the vertex is at 4, 2, 1, 2, 3, 4, 2. And remember, that's a major distance for our graph. It's the part of the box that we've been using, and since we went to the right to get there, that's r sub x. And counting that distance over, we're going 1, 2, 3 units. Now, that happens to be A. If you need to know, because it's in the same direction as the focus, you can think of it as A if you need that. All right. So let's start writing the equation. We actually know a lot of stuff that we can use. Since we're moving in the x direction, that means which variable will be in the positive fraction? Well, the answer is the x will be. So it will be x minus h. Do we know h? Yeah, it's the x coordinate of the center. That's 1. Divided by r sub x squared. Do we know r sub x? Yes, it's 3. So that's 9. Minus the quantity y minus k. Do we know the y coordinate of the center? Yes, we know it's 2, so it's y minus 2 squared. Do we know r sub y? Well, in my picture, I don't have anything in the y direction from the center, so let's say that's, for right now, that's unknown. I don't know what that is. Equals 1. So at this stage of the game, there's only that one unknown. So if we think about the fact that we have been given c indirectly, we know that the equation for c squared, for the hyperbola is a squared plus b squared. So since we know that c is 5 squared, or 25, is equal to a squared, 3 squared is 9, plus b squared, which we don't know. Now, if I had accidentally substituted 3 in for b and left a as the variable, I would still get that the variable squared, no matter which one of those I chose, is 25 minus 9. So it's actually immaterial if you think about it, whether you realize that that is supposed to have been called a for the r sub x or b for the r sub x. It doesn't matter, because you'd still get that the other variable squared is 16. And that's actually as far as we need to go, because now that we know that, oops, sorry, that messed up for a second. Here we go. The only piece of information we needed was the value of r sub y squared, which we just solved for. So everything that we already found is not changed. I'm just copying down what we already had. And where the r sub y squared is, I'm going to put in 16. And voila, we're done. Okay. So this is the kind of problem that you will probably encounter, where you're asked to write the standard equation, the equation in standard form, and I'm going to add to the directions and have us go ahead and find everything. So this is going to be a everything I might ask you kind of problem, although the question didn't ask it. This is, I think, worth our time. I'm having trouble getting that to go to the right spot. Let me try that. Okay, there we go. All right, so here's the equation. 9x squared minus 18x minus 4y squared minus 16y equals 43. This is already in the form I would want to start with. The either x or y, whichever one is given first. In this case it was x. Get all the x's together and all the y's together, and the constant 43 is already on the right side. So I think I'm already happy. Now to get it in that form where it's fraction minus fraction equals 1, that fraction has to have x minus h squared over a number. Same thing for y. So we're going to have to complete the square. That's hopefully you've kind of noticed that's a pretty important tool in this section. So to complete the square, the coefficient of your squared variable must be positive 1. So I'm going to factor off 9 from the x things and leave a space to complete the square. Then I'm going to factor a negative 4 off of the y squared, and this is probably one of the biggest tripping points my students encounter, is that when you're factoring off a negative 4, you have to remember that you're dividing negative 16 by negative 4 and getting positive 4y. A sign error there of minus 4y is what a lot of people accidentally do. Be very careful you're not one of those folks. Okay, and again, leave space for completing the square. I don't know why that 3 doesn't complete half the time. Alrighty. So, completing the square for x, half of negative 2 is negative 1. The square of negative 1 is positive 1. Keep in mind that what I've done is I've actually added 9 times 1 to the left side. So I need to add 9 plus 1 to the right side. I know that you can do 9 times 1 in your head, but please, if you write this down, you're making sure you're not forgetting something. So I know you can do that in your head, but if you write it down, it's probably better off for you. Then the number that completes the square for y would be half of 4 is 2. The square of 2 is 4, so I'm adding 4 inside the parentheses. But what I've really added, actually subtracted, is I've subtracted 4 times 4. So I need to subtract 4 times 4 on this side as well. Another common mistake is to add over here, and because there's a minus in front of that parenthesis and in front of that 4, you have to subtract on the other side as well. Lots of sign error problems that people get into, so be very, very careful. All right, factoring leads me to get x minus 1 quantity squared with a 9 out in front, minus 4 times, and then factoring that, I get y plus 2 quantity squared. And the arithmetic gives me 36 here. Then, of course, I want fraction minus fraction equals 1. So to make that turn into a 1, I'm going to divide everywhere by 36. Oops. Of course, you know we're actually dividing both sides of the equation by 36. We're just distributing that division over the subtraction. Just a little fine point there, but I think it's worth saying. Okay. Luckily, these numbers are nice. It's a nice textbook kind of problem because 9 and 36 cancel nicely, leaving what number in the denominator? Right, it's 4. Then the 4 and the 36 cancel, leaving what in the denominator? You're correct, it's a 9. This is one of those problems that it's kind of unfortunate that you see enough of these in textbooks that you think, well, it's always just going to be switch. And we said this with the ellipse as well. Just switch the coefficient to be the denominator of the other fraction. Well, I hate to burst your bubble, but that's not a thing. So be careful that you don't think that's a thing. Actually do the division and think through the arithmetic correctly. All right, so let's find out what we can. The center is at 1, negative 2. The x radius is square root of 4, which is 2. The y radius is the square root of 9, which is 3. At this point, I like to do the asymptotes next when I'm supposed to find them, because I now have everything I need to know to find the equations of the asymptotes. This is a good place to put that. So y minus the y coordinate of the center, so y minus negative 2, aka y plus 2, equals plus or minus r sub y over r sub x. Remember, it's r sub y rise over r sub x run. 3 over 2 does not reduce, so I'll go ahead and just write 3 halves, times the quantity x minus the x coordinate of the center, 1. Okay, so let's go ahead and find c. The equation for c squared is a squared minus b squared. So that's going to be, I'm sorry, I said that wrong. For c squared, it's a squared plus b squared. So that's going to be 4 plus 9, or 9 plus 4. Obviously, it doesn't matter what order you add those in. Technically, I'm doing it technically correctly, but if you reversed it, it wouldn't really matter in the end. And so here we get that c is the square root of 13. All right. I want to find the vertices and foci in a minute. Excuse me. But I want to start with the graph. So, because a lot of times I find those other points while I'm graphing or after I've graphed because it just seems easier to me. So our center is at 1, negative 2. We're going to go in the x direction 2, so 2 to the right, 1, 2 to the left. Our y radius is 3, so we're going to go from the center up 1, 2, 3, and down 1, 2, 3. Excuse me. So let me draw on those dots that we get. Go in the x direction 2, so right 2, left 2. We're going in the y direction 3, so up 1, 2, 3, down 1, 2, 3. Then we're going to draw the box that uses those points as the midpoints of the sides of the rectangle that we're drawing. Okay. Then draw the diagonals using a straight edge for this rectangle. Draw the diagonals. Okay, let's see. Get this going. Oops. No. Again, straight edge would have been so much smarter. If I knew how to get one in this program, I would do it. All right. Then we can actually right now, while we're thinking about it, we're about to start drawing. Excuse me. We're about to start drawing the branches in. So we're going to be actually finding which points are the vertices, because they're the points that are already on the graph right now that we use to draw the branches. So we're going to write these as soon as we start figuring out how to graph. That's how we're going to go. So to decide whether you're going to go up and down or left and right, what variable is in the positive fraction? Well, that's x, which means we're going to move in the x direction to get to the vertices. So this red dot is a vertex, and this red dot is a vertex. So what are the coordinates of those? Well, the first one I pointed to, 1, 2, 3, negative 2. So 3, negative 2. I'm just counting off, just plotting think about how those points are plotted. And the other one is negative 1, negative 2. Okay. Now that we found the vertices, we can go ahead and talk about the foci, and you can plot them if you want to. I'm not going to require that. We're going to start at the center and go in the same direction. We went in the x direction to get to the vertices, so we're going to change the x coordinate. So we're going to start at the center, 1, negative 2. Notice I'm leaving a little space after the 1. And what I'm going to do is I'm going to add and subtract the focal length from the x coordinate, which moves, boy, I did not leave enough room there. But anyway, it moves from the center left and right. So let me write over here. You wouldn't need to write this twice. I'm just writing this again, more spread out so that you can see it. And as I said before, you need not, when there's a radical after the plus or minus, split that into two separate points. I'll let you use the combined notation when it involves radical. Okay, and so you could plot that. Square root of 13 is somewhere between square root of 9, 3 and square root of 16, 4. So somewhere between 3 and 4. So if I went somewhere between 3 and 4, right, 1, 2, 3, 4 is about right there. And 1, 2, 3, 4 is about right there. Again, I'm not worried about perfection there because we're not really grading that. But at any rate, now draw the branches going closer and closer to the asymptote. And these, of course, because x is in the positive fraction, are opening to the left and to the right. That's something to pay attention to. All right. So, I think that's everything. Can't think of anything I might have left out. Nope, all looks good. All right, so that is hyperbolas, and that ends this lesson. Let me turn this off. Have a great day.